polynomial functions. In this section, what we're going to do is just dive a little bit deeper into different functions and see if we can figure out their characteristics, how they behave, how they act, and how they're similar. The first thing we want to do is look at some characteristics that they have, known as they are continuous. What does it mean when it says that it's continuous? It means that there's no breaks, holes, gaps, and basically no problem spots. In a very elementary sense, we would say that we could draw it with maybe picking up our pencil. So you can see in this first one that if I were to draw this function, it's very connected. It would go on forever in both directions. There's no breaks, holes, gaps, no problem spots. So this one is continuous. This next one, you can see if I went to draw it, I would come down, loop up, and then I would have to pick up my pen and pick up here and come down again. So we have a really big problem area right here in the middle. It has a break. And so we would say this is not a polynomial function because it is not continuous. Another characteristic that it has is that it's smooth. That means that it has rounded turns. So again, let's just look at how we would draw this function here. I come up and I would turn, come back down. Okay, a little bit turn, come back up, rounded turns. So this would be a smooth function, also polynomial. And this next one, sometimes it helps just to have a bad example. So when I go to draw this one, you can see that I would come down and then I would sharply go up. So really this is the problem area. It's not smooth. It's not a rounded. So we can't have this. Let's just write it out. No sharp turns. And so this would not be a polynomial function. So just some basics in dealing with a graph. Let's kind of go into the nitty gritty and let's look at the equations of polynomial functions. This right here is just a generic equation. I want it to write the generic equation up here, and then we'll also pull and do some examples from it. But looking at a generic one, we just kind of write it where we start with some n degree. We go down by 1 until we get to squared, first degree, and then this is like you had x to the 0 power, which makes the x go away. So very generic. But the reason I wanted a generic one is so that we can point to the things that I want to identify, and then we'll look at some numbers, some more examples with the numbers plugged in. So what I want to pull out of this is first this idea of degree. This highest exponent is known as your degree of your polynomial. And so maybe we could just write out beside it the highest exponent. Now, sometimes they're going to be kind of tricky and they'll not put them in order. If it's in standard form, it is at the front. But that's not always the case because they want to make sure that you look throughout the highest, look out every single term, because these are all known as terms, these things being added together, and find the highest exponent. And that's the degree of your entire polynomial. Then when you look at this as a whole, this piece with the highest degree on it, this is known as the leading term. Because in standard form, it would be at the front. This coefficient or number that's being multiplied by it, this is your lead coefficient. Lastly, I just want to identify here, this very last piece here without a variable on it, this is known as your constant. Now, what's the point of all this? Well, the thing that we want to do is we want to kind of take baby steps as we walk through this. I first want to identify some things, and then you'll see the results and why we need to know this information. So let's just kind of look at some examples and identify some of these objects. And so it says determine the degree and the leading coefficients. And so we're going to be looking at the degree of each of these examples and the leading coefficient. Now I'll write them out here, and then in the next examples, we'll just abbreviate to degree, leading coefficient. And so what you're going to do in each of these problems is you're going to first look for the leading term, or the term that has the highest exponent on it. So I look throughout here and I go, okay, well, I have a 6th power, 5th power, 4th power, 2nd power, 1st power, no power. What's the highest one? This is my leading term. What is the degree of this whole thing? It's just that exponent. What is the leading coefficient? It's just number 5, that large number in front of it. Let's go to the next one. You see, really quick. The next one, you look throughout the whole problem and you find the exponent. So no exponent, squared, cubed, 1st power, and then I'm going to take the largest one. And this right here is my leading term. Its highest exponent is a 3, so that's my degree. My leading coefficient is -4. See how this is working out? Next one, I look for the highest exponent. It's a 3. Now make sure you grab that negative in there. So excuse me. Highest exponent is not 3. Make sure you're paying attention. Highest exponent is a 5. And so this is the degree 5 with a leading coefficient of 5. Now, this degree is coming from the exponent. This leading coefficient or large number in front is the leading coefficient. They just happen to be the same number. Just want to emphasize that I was not just using one or the other. Next, we look for our highest exponent. So that would be a cubed, so a 3. Now, this is an assumed 1 here, so our leading coefficient would be -1. And you'll have some homework problems like this where you just identify these individual pieces. Now, other things, so we know that a function can be continuous. We know that a function or a polynomial can be smooth. We can find its degree. We can find its leading coefficient, its constant term. But what else can this tell us? Okay, I can identify it, but why do I need to know that? This leads us into our next part. Number of x-intercepts and turning points. So the number of x-intercepts, we've been looking for those, where it crosses the x-axis is at most n x-intercepts. And what n are we referring to? We're talking back to degree. N was the degree of our polynomial. So that's what that number is going to tell us. At most, how many x-intercepts could we have? And then what are turning points? The number of turning points are at most, how many would we have? N minus 1. Again, this n is coming from your degree. Now, in order to see this, let's kind of look at an example here. So we've got this equation of x to the 4th minus 4x squared plus x plus 1. So first I look for what is that degree? It's a degree 4. So that means it will have at most, since n is equal to 4, it will have 4 x-intercepts. And at most, 4 minus 1 are equal to 3 turning points. And let's see if that's true. Based off this graph, we can see that 1, 2, 3, 4, those are my x-intercepts. And then turning points, we have 1, 2, 3. That's where it turned. See, we made one turn, another turn, another turn. That's where we get that 3 from. And so lots of information can be grabbed from just looking at those values. Let's continue these examples and application. It says, without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points. So again, we're just looking at the equation and pulling information. So when we're doing this, just like with degree and leading coefficient, I have to find that lead term. So here's my lead term. And here's my degree. So since my degree is 9, that means I'm going to have at most 9 x-intercepts. And we'll do 9 minus 1, so 8 turning points. And again, we're just identifying information. And this is all at most. We may not have that many when we go and look at the graph, but this is how many we can expect at most. Next example, again, look for your highest exponent. That's 12. And so I would say, okay, well then since n is 12, I will have at most 12 x-intercepts. And we'll do n minus 1. So 12 minus 1 gives me 11 at most turning points. Okay, so lots of information can be grabbed from that equation. It's not a matter of just run and put it in some kind of graphing, but a matter of looking at your data and being able to pull out these characteristics. Now we're going to take a break from kind of identifying this, and let's just kind of go back and look at some parent functions. So when we look at just basics of what these polynomials will look at, we're going to look at power functions or the monomial functions, and we're just looking at what does f of x equal to x being raised to some power do? And then we'll add in our other pieces later. So first of all, we're going to look at this, and we can see that when we are looking at x being raised to some power, and again, these are just looking at the parent functions for polynomials, just kind of the parents, so the most basic pieces. When n is even, it's going to be similar to x squared. And so what's going to happen is, and I've got 4 of them graphed here just kind of show you, you can see that they're all facing upward. You can see that this red one out here is my x squared. We know what that graph looks like. It looks like a U shape. And what's going to happen is, as we increase the exponent 2, 4, 6, 8, we can notice what happens. As n increases, the graph, we can see it's still facing upward. It still kind of has that bowl shape, but it gets flatter around the origin, but increases faster, making it thinner. And let's see why this makes sense, because if I'm plugging in values right here for this x to the 8th, that means when I get to 2 to the 8th, that means it's going to jump up in those y values even quicker. And so this is your x to the 8th, this thinner one. But you can see it was getting flatter here at the origin. Now what's going to happen when we look at the odd one? Well, your odd one is very similar to an x cubed. And the same thing is going to happen down here. So you can see you've got your x cubed there in the middle. And this is your black equation here. And then as x is increasing in power oddly with the 5, the 7, the 9, that's where you're going to grab this green function on the inside, keeping our colors the same here. That's your x to the 9th in here. So it's going to be increasing on the outside. You can see that it's a little bit flatter in here by the origin. And so knowing how your basic parent functions for polynomials are going to react is going to tell us another characteristic. And this leads us into the leading coefficient test, or the long run or end behavior test, just depending on what question you're reading. And we can base them into 2 different groupings here. We can say, okay, well, let's look at when n is odd. When n is odd, it's going to be similar to x cubed. That's important to note. And when n is even, just like what we did before, it's going to be similar to x squared. Now, this is where being able to identify those degrees and coefficients are going to come into play. Split into the odd degree and even degree, but it's going to split even more when we look at these 2 facts of what is the coefficient? Is it positive or is it negative? And the same on the even. So what we're going to do is we're going to relate it back to what we did with our parent functions and understanding. If we know that the parent function x cubed looks something like this, then that means when we're looking at an odd power and a positive coefficient, it tells us that the end behavior is going to look like this, meaning as x is going to negative infinity, so as we move out this direction, we can expect the graph to drop downward. So we would say that f of x goes to negative infinity. And then we would say, okay, what is it doing as x goes to positive infinity or moves this direction? So we say as x goes to positive infinity, just putting the plus on there for emphasis. What is f of x doing? It's going upward, or it's going to positive infinity. Now the negative coefficient, what does it do? We know that a negative in the front does a reflection, so this negative right here is going to flip what we know about an x cubed. And again, this is just going to tell us the end behavior. It doesn't tell us what's going on in the middle. It's just telling us what's going on in the ends. That's why it's known as the end behavior test. And then we could write our notation from there, talk about which way is x going, but just knowing how to draw your pictures is going to help you to figure out what the behavior is doing. We can do the same thing with our even function. So when it has a positive coefficient, it is similar to an x squared, which looks like this. And again, we're just looking at the end behavior. So we're not even looking at what's going on in the middle here. It could have many curves just depending on what else is in that equation. But again, we're just looking at these arrows here and we're saying, okay, well, as x goes to positive infinity, so that means as it's going this direction, what is your y value doing? And it's going upward. So I would say f of x is moving to positive infinity. As x moves to negative infinity, what's happening with your y's or your f of x's? And so as x goes to negative infinity, so this direction, we can see it's still going upward. Now what happens when we put into this negative? Remember, that's a reflection, that's a flip, so that means now it's going to be flipped downward. And again, we don't know what's going on inside of here. It could have many loops or curves. But what we just want to know is what is the end behavior? What are those arrows doing? So now that we kind of have a template, let's look at some examples. I think this will clear up some confusion. It says, describe the end behavior for the following functions. So the first thing you're going to do, like we did earlier, is find the degree. The degree is 3. This degree is odd. So we're going to be looking at this left-hand side here. And then we're going to look at the leading coefficient. It's -1, so it's negative. So if it's odd, it's either going to be similar to the x cubed, facing this way or this way. And the way I tell the difference between these two is, notice if I connect the left and right hand behavior, this looks like it's going downward. This would be your negative version. This is going upward, so this would be like your positive version. And because our leading coefficient is negative, I want the one on the left here. So the question would say, as x goes to negative infinity and x goes to positive infinity, it wants to know what's happening to the y's. Well, as we go to just looking at my simple picture I've drawn here, as x goes this direction, you can see it's going upward. So I would say positive infinity. As x goes this direction, I can see that it's moving downward. So I would say negative infinity. And this would be the answers that they are looking for. But you can see how helpful a small little picture can be in this situation. Let's look at the next one. Again, we're going to start with the degree. The degree is +4. So that means it's an even degree. So that means it's either going to be facing upward, like a parabola, or downward. Then you look at the leading coefficient. And this leading coefficient is a +2. Because it's positive, I want to choose the one that's facing upward. So this is a small little drawing of what I can expect to see. So I'll say, okay, the question asks, as x goes to positive infinity, what's going on? And as x goes to negative infinity, what's going on? So the part that we're going to fill in is right here. So as x goes, just using my drawing, as x goes to positive infinity, we can see it's going upward. So that's positive infinity. As x goes to negative infinity, it's also going upward, so it's also positive infinity. Last one. Lots of pieces going on, but let's look at it. It has a positive 6 as the highest degree. Again, look throughout the entire problem. And then its leading coefficient is a negative 1/2. So that means it is even and negative. So that means it's either going to be facing upward or downward. Because it's negative, we're going to use the one that's facing downward. So this would be as x goes to positive infinity and goes to negative infinity, and then we'll fill out our f of x's. And so then I'm going to say, okay, as x goes to positive infinity, you can see these are both going down, so both negative infinities. So the leading coefficient test is going to tell us the end behavior. Now we've covered a lot of different characteristics here. Let's just kind of put this all together and talk about the whole picture that's going on. And we're going to look at different ways that we can do this. It says, given the graph of the polynomial function, determine the least possible degree of the polynomial and whether it's even or odd. So first, let's look at its turning points. Remember we talked about turning points are right here, right here, right here, where it's changing from increasing to decreasing. So we have 3 turning points. X-intercepts, we have 1, 2. So we have 2 x-intercepts. Let's see. We can also note that as we go in this direction off to positive infinity, it's going upward. As we go in this direction as we go to negative infinity, it's going upward to positive. As we're going to the right to positive infinity, it's also going upward. So the fact that they're doing both going upward, I can tell you that this is going to be an even function. So tell whether it's even or odd. Since the turning points were 3, remember turning points is equal to n minus 1, and we got 3. So that means n is equal to 4. Now you can see we only had 2 x-intercepts, but remember x-intercepts were at most. And so we're going to use our turning points to go backwards. So we can say that this is going to be at least a 4th degree. It's going to have a positive leading coefficient because it's facing upward. And it's going to be an even function because they're going in the same direction. So that's very interesting, all this data that we can pull just from a picture now. Let's look at some more information. It says, given the following functions, determine the end behavior, the maximum number of real zeros, and the maximum number of turning points, and the x and y intercepts. So lots to break apart here. First of all, in order to all do this, we have to look at the leading term. Here's our leading term. So this tells me that this is going to have a degree of 3. So that means x-intercept wise, we could have at most 3. Turning point wise, we're going to have 3 minus 1, so 2 turning points. Looking at the degree being 3, this tells me that it's odd. And then I'm going to look at my leading coefficient. It's a positive 2. So because it's odd, we know that it's going to look like this or this. Because it's a positive 2, that means when I connect the left and right, it should look like it's going upward. So my end behavior means that it would be going down over here and up over here. So it says, given the following function, determine the end behavior. We can see that with our green arrows. The maximum number of real zeros is 3. See that here from our at most x-intercepts. The maximum number of turning points, here it is at 2. And then it wanted us to find the x and y intercepts. So this is where our solving is going to come into play. To find the y-intercept, remember we set x equal to 0 and solve. So I would say, okay, that's f of 0 is equal to 2 times 0 cubed minus 6 times 0 squared minus 20 times 0. That just gives me a value of 0. So that means I'm going to have a point right here of a y-intercept at 0, 0. Next, I need to find my x-intercepts. To find my x-intercepts, remember to find your x-intercepts, you set y equal to 0 and solve. So this gives me 2x cubed minus 6x squared minus 20x equal to 0. I can factor a 2x out, leaving me with x squared minus 3x minus 10 equal to 0. And then I could factor what I have left over. That gives me x and x, negative 5 and positive 2. And then I'm going to solve all three of these out. So 2x equal to 0 gives me 0, which we already knew by that y-intercept. X minus 5 equal to 0 gives me 5. And then x plus 2 equal to 0 gives me negative 2. So that means I'm going to have an x-intercept at negative 2, 0, and 5. I know my end behaviors, and putting this all together, I'm probably going to have some kind of curve that looks like this. Now that's just an estimation, but it tells me a lot about the graph just by looking at all these details of our equation. Let's look at this last one. I know you're probably got a lot of information. We're going to do the exact same thing. So we're going to start with our leading term, and this is this x to the 4th. So I know that my degree is 4, so that means it's even. My leading coefficient is a positive 1, so that means it's going to face upward or downward, and because it's a positive 1, I know it's going to be facing upward. And so I'm going to have end behavior looking something like this. I know that my x-intercepts is the same as my degree, so that's 4. My turning points is 4 minus 1, so I have 3 turning points. And then I also need to figure out my intercepts. So my y-intercept, set x equal to 0, gives me 0 to the 4th minus 4 times 0 squared minus 45. So it's negative 45. So I'm going to have a point at 0, negative 45. And then my x-intercepts is set your whole equation equal to 0. Now for this one, we're going to have to factor it. That would be x squared and x squared, negative 9 and positive 4, and then I could solve this. So I get x squared minus 9 equal to 0, so x is plus or minus 3. X squared plus 5 equal to 0. Now this one gives me imaginary. And imaginary is fine in the solving realm, but in the graphing realm, I'm not going to be able to graph those on this coordinate plane. So putting all these pieces together, we're going to kind of have to count this out by tens. So let's call this like 10, 20, etc. So to get to negative 45, that would be right here. And then to get to negative 3 and positive 3, looking at these two values. So just a rough idea of what this graph looks like might possibly be something like this. And I could fill in some more values to make sure that that's it. But I just want to kind of show you how we can pull all the information we've been doing together. So please go and attempt the homework and let us know if you need any assistance.